Maybe let's get started right away with the discussion. So let me just remind people how the discussion works. So I already mentioned yesterday, so you can check in the video of yesterday. But in very shortly, the idea will have 20 minutes that are totally up to Barton and Yuji to do as they please, followed by 30 minutes that should be a more informal discussion with the audience where people can ask questions, make comments, also ask questions to the previous speaker. There were many questions for Ashok that we could still ask during the discussion session. And please, during that part, so of course, keep your camera on if you are participating so that it becomes lively and informal and relaxed. And also raise your hand if you want to ask a question. And besides raising your hand, if your question is related to what we are exactly discussing right now, to the topic that is being discussed right now, wave or write in the chat so that we stay within the topic and then we move to the next topic. I think this is working well. So raise your hand and wave if your comment or question is related to what is being discussed at the moment. And I'm taking note that we are starting a bit late, and I will now count 20 minutes before we move into the informal part. So I give the floor to Barton or Yuji to do as they please for these 20 minutes.
All right. So I wish to thank, on behalf of Yuji and myself, our friends, the organizers of this nice conference, for giving us the chance to talk about what has happened with string field theory in the last few years. Next. So I will take a very restrictive viewpoint of achievements. I will consider instances where the string field theory has helped provide the answer to some specific physical open questions. The set of achievements of string field theory include other things in which, for example, from the early start, the role of the BRST operator was brought forth by string field theory, and many other things having to do with Riemann surfaces, exotic algebras, BV quantization. But let's first talk about physical questions. So perhaps the most dramatic application of string field theory was to the subject of tachyon condensation, where Ashok Sen had a set of tachyon conjectures having to do with the depth of the potential of the tachyon, having to do with the mass of the D brane, with solitons, D branes as solitons, and the fact that at the tachyon vacuum there would be no excitations, and worked in string field theory, established these conjectures first numerically and then analytically through the work of Schnabel. And it's important to emphasize that those results are non-perturbative. So it was evidence that certainly the string field theory, the open string field theory, does contain non-perturbative information. Next. So the second point is that we come to realize that string field theory is the first complete definition of string perturbation theory. The first quantized worldsheet formulation works in many standard circumstances, but in some cases, it doesn't quite tell you what you're supposed to do. This has to do with infrared divergences and S-matrix elements for states that undergo mass renormalization. So in a series of papers, and we heard some of this today, Sen and collaborators have pushed this interpretation and used string field theory to compute one loop mass renormalization of unstable particles to fix ambiguities in two-dimensional worldsheet string theory. And today, as we heard, to fix the normalization of type 2b D instanton amplitudes. Next. So let us talk about what has happened in the last few years. And there's two very important things that we have in these transparencies. First, following from the solution of Martin Schnabel, we have learned how to write analytic solutions that describe general boundary conformal field theories. That is, you start with a standard open string field theory in some particular background. And you can write now, thanks to the work of many people, but mostly Erler and McAfee, a solution that describes a different D-brane configuration, starting from some canonical D-brane configuration. So this shows, again, non-perturbative information in that seems like open string field theory captures the landscape of solutions and some notion of physical background independence. That is, you can reach other backgrounds at least through solutions, even though the background independence is not manifest. And the second important thing is that the superstring field theories had a number of technical difficulties that prevented their construction, but they have finally been constructed. And for the open superstrings, we have these three works shown here. Next. And for heterotic and type 2 superstrings, that is an even harder problem, there was a complete solution in which Ashok Sen used an extra copy of the string field. So there were, usually you have just a single string field in whatever sectors, NS, R, NS, RR, but now you have an extra copy, a complete doubling that turns out essential in order to be able to write an action, and you can show that this field decouples. So the action is written there. That is the action for a type 2 superstring field theory. It takes the same form for a heterotic, depending on how you define the string fields. And there's psi, the traditional string field, and psi tilde. There's a picture changing operator G in the kinetic term for the auxiliary field, and that's it. So in fact, for the first time, we have now string field theories, covariant string field theories for all of the string theories. Next. So from the geometric viewpoint, in any string field theory, there are algebraic issues that you have to resolve, and there are geometric issues. If you want to define off-shell amplitudes, which is what really a string field theory does and helps you for doing any kind of analytic continuation and all the work that you need to do, you need string vertices. Those must satisfy a geometric version of the Batalin-Vilkovitsky master equation. So there's been some progress in this direction as well. Here, the goal is to find the simplest way of having string vertices. For the case of the open string, at least for the classical theory, the Witten vertex does the job. For closed strings, we know this is a lot more complicated. But minimal area metrics in the past have been used for open string field theory and for the classical closed string field theory. We didn't know for a long time whether those minimal area metrics would exist for higher genus or how they would look. But in fact, now, work I've been doing with Hedrick, using convex optimization tools that also help in holography, now you can find some of those metrics. Next. This, for example, is a picture of a torus, a square torus with one puncture. The puncture is at the center, and there's bands of geodesics, red and blue, intersecting, and there's curvature, and it's a very non-trivial minimal area metric. And these metrics now are known to exist, at least in some cases. Next. The other direction, we heard in a previous string conference for the attempts of using hyperbolic geometry, a very developed branch of mathematics, to discuss modular spaces of Riemann surfaces. This was done by Musevian and Pius in 2017. Together with Costello, given a definition of exact hyperbolic vertices, that they have been extended to open closed string field theory by Minjiao Cho, and some analysis of the three-string vertex by Firat at MIT. And basically, I show in this picture a three-punctured sphere. In a sense, on the left is the approach of Musavian and Pius. The off-shell three-string vertex is defined by the middle region with these three red boundaries that represent the off-shell states. And in the new proposal of Costello and myself, the pants diagram is the one that does the definition of the vertex, and it has a very natural generalization due to the fact that moduli spaces can be constructed by gluing pants very easily. So as Pius and Musavian emphasize, it's conceivable that the advances in mathematics in hyperbolic geometry could allow some computations to be done in this picture that were not possible in other pictures. Next. So another thing that has been work in string field theory in the last few years is establishing some field theory results that follow once you have a string field theory. An important remark and observation has been given by Pius and Sen, in which they noted that string field vertices have these exponential factors, off-shell factors, for all the lines that come off of a vertex. You have factors like this. And these factors, the momentum, the spatial part of the momentum leads to convergent integrals, while the energy part of the integral is divergent. So in Feynman diagrams in string field theory, the prescription for doing the loop integrals requires that these loop integral contours approach plus minus I infinity. There's an I missing there, I'm sorry. Finally, when you analytically continue the external momentums back to the real axis, the contour is not rotated, but is kept fixed at infinity, and singularities may push it around. With this definition, there's an analysis of unitarity that has been carried out, analyticity and crossing symmetry, and some discussion of Wilsonian action. Next.
You used more or less half of the 20 minutes, like 10 minutes.
Yes, and now Yuji goes on. So Yuji, please continue.
Okay, so I'd like to tell you that homological perturbation theory of homotopy algebra is playing an important role in recent directions of research on string field theory. So traditionally, homotopy algebras such as A-infinity algebra or L-infinity algebra were used in the construction of string field theory. And the most important example is the construction of closed string field theory by Barton in this paper. Recently, homotopy algebras are used in different contexts. As I'm going to explain shortly, the construction of the low energy effective theory by Sen, so we see the homotopy algebra playing an essential role. Also, there are many papers on the relation between the on-shell scattering amplitudes and the so-called minimal model of homotopy algebras. But let me mention one paper which is very relevant to us by Kajiura. So let me very briefly explain the A-infinity algebra as an example of homotopy algebras. The A-infinity algebra describes relations among multi-string products of open string fields. So let's consider an action of this form where interactions are written in terms of multi-string products, two-string product V2 and three-string product V3 and so on. Also consider the gauge transformation in terms of the same set of multi-string products V2, V3 and so on. Then this action is invariant under this gauge transformation if multi-string products satisfy a set of relations called A-infinity relations, given these. So let me explain in the context of low energy effective theory. So then the path integral over massive fields to obtain the effective action for massive fields generates new multi-string products For example, from these three string vertices, we get effective quartic interactions in the low energy. Here, the integration, here the propagator for the massive field. But the important point is that the infinity structure in the original theory is preserved in this path during the process of this path integral. And the homological perturbation theory provides a fairly explicit construction of this infinity structure in the low energy theory, or infinity structure in the scattering amplitude. So then multi-string products satisfying the infinity relations can be efficiently described by linear operators acting on this vector space. This is a one-string Hilbert space, two-string Hilbert space, and so on. The infinity relations can be compactly expressed in terms of a linear operator M on this space, which square to 0. So the complicated relations can be written like this. So very efficient, right? So for the action of open bosonic string field theory, the infinity structure M described by M is where M is given by Q plus M2, where Q is associated with the BRC operator, M2 is associated with the two-string product, which is the star product. Then the homological perturbation theory provides M for the effective theory as follows, where P is the projection, and the H is for the propagator for the massive field. So this inverse is defined by the geometric series as usual. So this is fairly explicit. So let me give you some examples from recent string field theory papers. There are also field theory papers as well. Based on the general framework developed by this paper by Irvin, McAfee, Schnabel, and Boschmeyer, McAfee and Boschmeyer explored cross-string deformations in open string field theory, such as the change of the compactification radius of S1 compactification in the series papers. And Euler and Matsunaga discussed mapping between Witten's covariant string field theory and light-cone string field theory in this paper. And together with students of mine, I considered gauge invariant operators of open bosonic string field theory in the low energy limit in this paper. As you see from the title of these papers, the motivations are totally different, but essentially the same tool from the homological perturbation theory here is used in these papers. Furthermore, homotopy algebras can be also useful in ordinary quantum field theory because basically Feynman diagrams here can be handled algebraically in this approach. And I took figures from this paper by them and Spiranaro-Lakis. So these two-loop diagrams can be generated by this kind of geometric series like this. So we can handle these Feynman diagrams algebraically. So I would expect fruitful interactions among various research areas. So now let's move on to the section of the open questions. So Barton, would you explain the first two items in the list?
So let me take these first two questions. Some things that have remained still unsolved in the last few years are the question of initial value formulations in open string theory and closed string theory, perhaps more seriously. And there was work by old work of Eliezer and Muller pointing all kinds of potential difficulties with higher derivative theories and initial value formulations, and an interesting discussion by Euler and Gross, but still the issue is not completely clear. And this shows in the ideas of microcausality and causality. In fact, microcausality, usually defined as operators commuting when they are separated by space-like intervals, is difficult to test in covariant string field theory, which is a path interval formulation of the theory. And perhaps a formulation of Bogolyubov could be useful in doing this. As we appreciate the role of initial value formulation and the causality that has infinitely many time derivatives in the theory and infinitely many space-like derivatives, this is also related with non-locality, which would be very useful to understand better, as it has been repeatedly suggested that the black hole information puzzle is hard to resolve in the framework of low energy effective field theory that is local, and you need some kind of non-locality. Another thing that is sorely missing is classical solutions of closed string field theory. Just like the open string field theory, I would suspect that these solutions exist and contain non-perturbative information. You can go from one background to another. But it's still, since the theory is more complicated, nobody has been able to find those classical solutions. Of course, if the theory was reformulated, perhaps that would help. Next.
So let me explain the next item. So which is the proof of the Adseot correspondence. I have made this intentionally provocative for this purpose of discussion session. So Adseot correspondence is typically realized in the low energy limit of the theory on D-branes. So you may think the theory before taking the low energy limit should be something like open closed string field theory, which would be difficult to be defined non-perturbatively. But I would claim that the open string field theory can do the job. So usually, open string field theory is sort of something that reproduces the on-shell scattering amplitude of open strings. But in this context, we are interested in the correlation functions of gauge invariant operators. Also, the 1/n expansion of such correlation functions should be perturbation theory containing gravity. So this kind of direction research has not been explored in the string field theory. That's my message for the future direction. So, and for this story to work, it is important that the important question is that whether or not the open superstring field theory is a consistent quantum theory. So if this is the case, I think we can use it to help prove the Adseot correspondence in the framework of string field theory. And we have the last item in the list, but before going to the last item, let me show you something interesting. So let's see what Barton said 10 years ago. So there was a conference in Kyoto 10 years ago, which I also attended, so 2011. So Barton gave a talk, and the title is String Field Theory, Achievements, Challenges, and Future Directions, which is similar to the title of this discussion session. And at the end of that talk, Barton mentioned future directions, challenges as of 2011, 10 years ago. So the first, he mentions the missing string field theories. But as you heard from the Barton's part of this presentation, the missing string field theories have been constructed. Very nice. Then he mentioned that the missing analytic solutions, which have also been constructed. So we are really making good progress, right? Then he continued to say, but the question most likely to determine the future of SFT is a question of, guess what? Background independence. So we need manifest background independence. So Barton, would you like to say something about the background independence?
Okay, sure. Next. It's a difficult question, and I think one could say there's been a few attempts that were interesting, and they all look very exciting and promising, but didn't get too far. We don't know whether they're wrong attempts or we didn't have the tools, or perhaps we need something more radical. So one approach, Witten wrote some way of constructing BV master actions in the space of all open string worldsheet theories, not conformal theories. It did help for tachyon condensation, but eventually with non-renormalizable interaction for these worldsheet theories, it got very difficult and was kind of abandoned. I also had some very straightforward suggestion that the L-infinity algebras or A-infinity algebras would need the zeroth product, something mathematicians always include. So there you see a product of two string fields, that's standard. A product of a single string field is the linear operator Q, and a product without a string field is a special string field F. And if that string field F satisfies QF equals 0 and Q squared equal F, you could build a new kind of string field theory. But this had not been built and had not been studied. It's kind of difficult. Finally, from open string theory, people thought of using the tachyon vacuum as a very special universal background and formulating a vacuum string field theory using a BRST operator that just was built of ghosts. In reality, that works quite well, except that this purely ghost BRST operator doesn't do some things very well. Yuji actually did a very important contribution to this field, but at the end, it just got difficult. So I think we need a new idea that will come from some of the participants in this conference. That's it. Thank you, Yuji.
Thank you very much. Let's thank Barton and Yuji for setting up the discussion.
Yeah,
and
mention 1 second, Pedro. There's the string field theory yearly conference happening, and there will be one organized by Chakrabarti, Irving, Lipinski, and Vosmera in September, and we invite people to come and see.
Very good. So as I said before, please raise your hand if you have questions, and yeah, we can start with Nathan, perhaps. Yeah.
So I had a question, which is about just the definition of the string field. So, I mean, has there been much progress on trying to define the string field in some more abstract sense? What's an allowable string field? If you allow insertions in the string field and things like that. And I guess that's related to why does the level truncation method work so well? So I guess that's for everybody. I mean, not just for you.
Yeah, I'm not aware of any specific progress, but I welcome comments from other people. Level expansion remains a little mysterious, I think, why it works. It would be interesting to see how it would work in a theory that has more than a cubic interaction, a theory that has a cubic, quartic, quintic, and I don't think there's any suggestions how you balance level versus the power of the interaction as well. People that understand maybe how the string field is defined, maybe Carlo Macaferri and Erler, that have been doing very interesting solutions in the space of open string field theory, may want to comment on this. I don't know. Or Yuji.
Yeah, it's a very difficult question, so I don't have much to say, unfortunately.
So again, if you have a comment about a particular question that's being discussed, wave and I'll figure out. Otherwise, if Nathan's question is too hard, we'll move to Shi.
So I'd like to make a comment. In fact, it's something I wanted to say in a discussion next week, but I think now is the appropriate time to start talking about string field theory. An application that has not been mentioned so far, which I think is important, is that the superstring field theory, closed superstring field theory, provide a first principle definition of remote flux background. In my opinion, it's really the only available first principle definition of our flux background beyond the low energy approximation. The alternative, for example, one sometimes talks about the Green-Schwarz string in our flux background. this to me is a effective action. The Green-Schwarz description is an effective action based on nonlinear realized space-time super Poincare symmetry or other symmetries in the ADS background, and it is subject to intrinsic ambiguity of higher derivative ambiguities. Now, in the case of say ADS 5 times +5, these ambiguities are the working hypothesis that they can be fixed by impulse integrability, but that's not from first principle. So I would even say that for strings, type 2B string in ADS 5 times +5, even at the level of an expansion in 1/r, 1/r radius, the only first principle definition of the string background, the low energy approximation that I am aware of, is to start from the Minkowskian background and turn on perturbatively a non-trivial solution to the closed superstring field NSR equation. And then you can linearize around that non-trivial solution and try to determine order by order 1/r of the string type 2B string spectrum ADS 5 times +5. In practice, this has not been carried out in that specific background, but in principle, to me, this is the only first principle way to determine the string spectrum in the background, and further on top of that, perturbative interaction.
So this has not been carried out in practice, or is it?
Yes, it was difficult. In fact, as far as Adseot tells me once that he has studied this at some point, but it was difficult. I mean, a few years ago, Scott Collier, Min-Jae Cho, and I did the analysis thing for ADS3. In that case, it was technically a bit easier because we're not changing the geometry of the background. We're just putting on R flux, and we can indeed understand correction of R flux on the string spectrum using string field theory. I mean, we didn't really use the hard part of string field theory. We used the framework, but we only did the leading order calculation, which does not require most of the technology of string field theory. But nonetheless, conceptually, it was a string field theory calculation. And for ADS 5 times +5, deforming from class space is technically harder, and this has not been done as far as I know. I mean, the thing is, people have studied this, of course, in Green-Schwarz formalism, but I would say that people have not gone to the high enough order in alpha prime expansion to encounter the ambiguity that would require integrability to fix from the worksheet perspective. In principle, based on NSR, there will be no such ambiguity, and it should be a first principle calculation. But that has, of course, not been actually done.
Maybe let's pass to Nathan. If I understand correctly, Nathan is waving. Waving is like this, Nathan. You are clapping. I think you want to wave. We use hand. So let's pass to Nathan.
I don't know if you're distinguishing Green-Schwarz from pure spinor, but I don't know why you think Ramond, let's use pure spinor formalism just because that's the one I like. Why do you think Ramond is more complicated than Never-Schwarz? I'm missing some point here.
I was thinking purely in NSR formalism. In NSR formalism with the Ramond background, I would say there's no known worldsheet local CFT that obeys the usual rule of worldsheet CFT that we know of. The pure spinor formalism, to me, there's a little bit missing, which is just the full consistency of the worldsheet CFT. But perhaps for the ADS background was not at least in the class space, because this issue of that you cannot close the OPE without trivializing the vertical homology, because there's in nominal formalism at least it's 1/λ bar singularity.
No, but sorry, we're just talking about tree amplitudes, right? You're just talking about classical. I'm not talking. I'm talking about let's say to begin with, even just determining the string spectrum, but to all ordering alpha prime. So this is a quantum worldsheet problem. Yeah, it's quantum on the worldsheet, but not in string loops. I mean, it's a classical.
That's right.
I think at the classical level, the sigma model is completely consistent. I don't think there's any question about the sigma model being consistent.
My perspective is that I want to work in a formalism where I at least know full consistency in perturbation theory to all order. And then within that formalism, I want to get the spectrum as a first step. Now, I'm not saying that there's no other way to get the answer, but I want to get the answer within a framework where all of perturbation theory is in principle as well defined. So that's all I'm saying.
Okay, I guess if you insist on string loops, then I agree with you. But if you're happy with just string tree level, so maybe I'll let somebody else talk.
Yeah, maybe let's pass it to Shota. Maybe he will tell us that integrability is the way to go instead of.
Well, by the way, like I see Leonardo is unmuted, so I thought like he might have something to say about this before.
I just had a very quick question for Shi, but whether in ADS 5 times S5 this will actually be a large. I mean, in your work on ADS 3 times S3, it was an infinitesimal deformation in principle you could turn on. But in ADS 5 times S5, would that be that, or you need really a finite deformation?
I was talking about specifically about 1 over R expansion. So
Okay,
what's perturbing 1 over R? But you know, we know that the answer is non-trivial perturbing 1 over R. So.
Yeah.
Yeah, go on, Shota.
All right, yeah. So actually, my question is not related to ADS 5 times S5 or integrability, unfortunately. So I just had some question about the last point about the background independence, and in which they showed like a vacuum string field theory. But I saw like as far as I understand, vacuum string field theory is for open string, like a tachyon vacuum for open string. Is there any like progress about closed string, about the closed string sector?
Yeah. So vacuum string field theory has not been done for closed strings. In fact, perhaps the most crucial question is the closed string tachyon vacuum has not been determined. And that, you know, that may be the thing that is really missing to understand much better the closed string field theory. We did try to calculate the closed string tachyon vacuum in the level expansion. You may want to look at those papers, but it was not very conclusive. It seemed that there might be a tachyon vacuum, but was never identified. So unfortunately, we have not developed enough analytic techniques to do the calculations of solutions in the closed string field theory. But you know, there might be some way to do it. It's at the end of the day, the geometry of the vertex it's quite flexible, even in the open string theory. So, so maybe somebody will, the group that has been doing analytic solution for open strings can finally find some solution for closed strings. It would be great.
I see. Thanks.
Mukund, by the way, Shi, if you still want to ask another question, or you forgot to lower your hand?
Oh,
but let's go to
I
Mukund now.
had a
Anyway.
question, but it was about the Adseot talk. So I'll ask.
Okay. Go on, Mukund. Yeah, go on.
Yeah, so I wanted to go back to something that Barton mentioned about the initial value formulation in string field theory. And in more general, I'm curious what the prospects are for understanding something like a local light cone in quantum gravity, which is not a meaningful concept. So usually what we tend to do in quantum gravity theory is just say we talk about asymptotic observables which satisfy appropriate causality conditions. But from much of the stuff that has been done, a lot of the rules of string field theory seem to follow very much from in line with quantum field theory. So I'm curious where the local structure of quantum gravity is buried in closed string field theory. So you mentioned a couple of things that could potentially be useful. I was wondering if someone had a comment on this.
I don't have at this point much to say, but I think this is a really important question. Basically, there's been efforts, I think, within the context of the black hole paradoxes to compute commutators of closed string fields or open string fields and figure out how they behave. Now, the computations at the free level, they're kind of not very interesting, and nobody could figure out if the definition of a light cone over an average form of the strings or other definitions should be used. It was kind of trivial. But then there were computations at the first ordering interactions. And they could only be done in the Lython. And in those cases, they found that somehow the commutator doesn't vanish for space-like separated points. And that has been a little confusing because certainly if there were gauge invariant operators, that shouldn't happen consistent with causality. But somehow it seems to happen, or maybe a background dependent phenomenon. So I actually think these calculations were done in the year about 2000, and I think they were not very detailed and they were not investigated properly, actually. So I believe they should be done again, and presumably the analogs in the covariant string field theory, which, as I was saying, since there's no Hamiltonian known for the covariant string field theory, they would have to be done in the path integral formulation. So I think causality has been very important for the bootstrap and for many things, and we really have not done justice to the computation of causality.
Thanks.
Maybe I will have a quick comment on what happened in tree level, or perhaps on perturbative string theory. But there's a paper about the notion that shock waves commute by Kologlu, Kravchuk, Simons-Duffin, and Zhiboydov. That is a very sharp statement about causality that makes sense in the so a simple example of a shock wave is the integral of a stress tensor like the ANIC along a null geodesic, and you can take space-like separated such things, and these things, and there's a sharp sense in which these things commute in string theory, at least in perturbation theory. So that could be a useful starting point.
Maybe you can post the reference in the chat. We'll look at it and try to figure out whether something can be done. Being in charge of the discussion, I don't know, I would like to maybe invite Martin Schnabel to say a few words if he wants, and tell us what he thinks is the future of classical solutions, or his field of expertise that he's done so much to advance. I know if he's there.
Oh, yes, I'm here, Barton. Hello, Barton. Thanks for starting nicely this discussion with Yuji. So, I mean, in my personal view, I think the outstanding challenge is to look for the classical solutions for closed string field theory. And in fact, this is one of the things that interests me the most at the moment, but the progress is slow, but I guess I'm optimistic that there is something to be done. Also, I like the Shota's question. I think this is also something that I'm thinking about with my students, and like trying to formulate the vacuum string field theory analog for closed string field theory. Yeah. Also, I may add an answer to the first question by Nathan that he asked in this discussion session. So whether like level truncation works in closed string field theory, my answer is not clear, because as you noticed in your work with your students, it was never clear whether it works in closed string field theory. And in the context of open string field theory, when he asked what is the space of string fields, the answer is not clear, because there were some very nice constructions in the 80s in the context of this purely cubic string field theory, some operators, some string fields that were supposed to behave nicely, but then it was found that they they're anomalous, they violate associativity of the Witten star product, etc. But analogous objects, but slightly better behaved, were used around 2005 in these analytic solutions. So that's my answer to Nathan. That was is not clear. So as far as I know, no one really did any good systematic work on what the good string fields are. Yeah. Barton, did I answer the question?
Thanks very much for those comments. You're happy to hear all these
So
things.
she seems to have something to add here. So he was raising his hand.
Yeah, so about the space of the string field, I mean, this is kind of a question / comment. So in the context of closed string field theory, where we construct the string vertices just order by order in the string field, the formalism is such that the closed string field is just a state in the worksheet CFT Hilbert space, with everything goes included. To me, this is, I mean, without even worrying about the normalizability and things like that. To me, the first kind of slightly unpleasant feature of this is that it doesn't have general coordinate invariance compared to low energy effective discriminant like supergravity, right? And in particular, if we want to describe something like a black brane in type 2 string theory as a solution to a closed string field equation, this already is a bit funny because if you work perturbatively, then it has a source, and you might say that okay, if we work away from the source, it's okay, and you maybe want to allow the solution, but then it would be hard to see the horizon, right? So unlike in supergravity, where the magic has to do with the fact that you can write a solution that has a horizon, and if you try to write analogous solution to closed string field equation, which by definition was a state, some funny looking maybe state in the original worksheet CFT Hilbert space, and this the presence of the horizon is extremely non-manifest, and yeah, so this to me is I'm not saying that there's anything wrong with it, but it's just kind of an obstacle with the kind of obscure some of the physics. Just a comment.
Well, it's
So we can move. Mukund is waving, or we could move to some other topic. Barton, up to
I
you.
just wanted to add a quick comment to Ji's question.
Okay, quick, so that
what I asked earlier, Barton, because to even define the horizon, you want some local, I mean, you can either say some statement about, you can talk about the event horizon if you have a stationary solution, and then you can say it's something associated with the asymptotic boundaries, causal path of future null infinity or whatever. But if you want to say some local notion, that's much more tricky, and exactly because of what you said, there's no coordinate, there's no covariance statement to make.
But just to follow up on that, I could imagine something slightly different, which is that, I mean, if you think about what we do in GR, of course, we just look at the geometry around the horizon, we change the coordinate and expand around there. I mean, I could, for example, if you think about B3 brane, black 3 brane solution type 2b, when n is large, I could imagine looking at down the throat and expand and view the throat as a deformation from a flat space locally. Right. So in principle, there's a way to approach that region. Now there's a question of whether you can, as a solution to the closed string field theory, expand it, where you look at near the throat versus looking at asymptotic flat region. Can you really show that they are the same thing, or can you really describe this as a true solution to the closed string field equation?
Yeah.
I don't know.
I don't know if Martin wants to say something about it in response to that, or if I were, he's thinking about these solutions, but certainly there are simpler solutions in closed string field theory that perhaps can be found first, which, for example, you have a 25-dimensional background, and then you put a minimal model in the last extra dimension, and you have a dilatant background, and you go from one minimal model to another minimal model. just to understand how the solutions are written. Writing solutions that have a intricate general covariant gravitational description might take a while. It might be very difficult at this moment, but that would certainly be the goal. And I just don't know to what degree those solutions would be understandable without a little bit more background independence. So I want to maybe, Pedro, I don't know if would be kind of interesting as well if Adseot Sen, that has contributed so much to this field, wanted to say maybe what he hopes for string field theory in the next few years. I don't know, Adseot, if I put you on the spot and get you to say a few words.
Yeah, I don't really know. I don't have much to say. Maybe I should say something that, I mean, often people are somewhat scared of string field theory because it looks very complicated. But my view of string field, at least one very conservative view of string field theory, okay, which doesn't aim very high, okay, is that if you think of world sheet theory, I think it has a lot of information, okay, but all the information is coded. Okay. And what I meant, say coded, I mean, what I mean is the following, that if you try to calculate anything in the world sheet description, it's divergent. You cannot put it on a computer and get a number out of it. Now, often what happens is that you can resolve those divergences either by using analytic continuation or by using I epsilon. But it doesn't always work. And from that perspective, I'd say that the string field theory, it uses exactly the same data that the world sheet theory does. But it's a very good decoder of what the world sheet theory is trying to tell us. I mean, the extreme example perhaps is the tachyon condensation, that all the data that went into the study of this level truncation is coming from world sheet calculation. Nevertheless, the string field theory turns it into some non-trivial result, right, which you couldn't get directly from the world sheet. And the other examples that Barton mentioned are probably just minor versions of the same thing, that it somehow takes the world sheet and decodes it. Okay? It tells us what the world sheet is trying to tell us. So that, I think, is the most conservative approach to viewing string field theory. Okay? But of course, it's possible that string field theory can do or will do much more than just decoding the world sheet description.
Great, thank you. I know, Pedro, if you call.
Yeah, I have a suggestion. Let's say we are officially over with this official discussion, and we'll stop the recording and we'll resume in 20 minutes. But we can continue informally, and in particular, Shiraz and Danielle could ask their questions, and we can continue a little bit more during the break for those of us that don't mind having a shorter break. But the official discussion, we would now thank Barton and Yuji and everyone.